students and some of my students whom you can see also in this group. Let's begin with saying something about ordinary measurement. Let's take the measurement of spin as an example of quantum measurement. There is a spin and we would like to know whether there is a particle, spin hat particle, and the question we ask is whether it's spin up or spin down. The way to measure it is, of course, to let it go through, that's the standard measurement. We let it go through a Stern-Gerlach magnet, such that if it's spin up, it is deflected to one side, and if it's spin down, it's deflected to the other side. And there are two detectors which register its path through this system. Simple measurement, and once we understand that, we can understand what is a weak measurement. That's the standard measurement. Of course, we know that what is so unique about quantum measurement is that the particle is, before being measured, is superposed. That is, it's not only that we don't know what is its spin, but its spin objectively is superposed. It's both up and down, and it's only through measurement that one of them becomes realized and the other vanishes, which makes quantum mechanics so unique. Now, there are a lot of problems with this kind of measurement. It's non-deterministic. We don't really understand what's going on there. There is something strange. You got playing dice and so on and so on. The last thing that you would think somebody would want to do in this case is to make the measurement less efficient. You would expect people trying to make the measurement as accurate and as efficient as possible. And along comes Iyar and say, perhaps we can learn something new by making the measurement weaker, much less efficient, and this is how it works. When you are making a weak measurement, when you make a strong measurement, then you know that the uncertainty with respect to momentum of the detectors is very low. That is, they have an imprecise position. You allow them to have to be superposed in terms of their position, but then you know exactly their momentum, and then you can compare the momentum before and after the interaction, and then you know the momentum of the particle. If you want to make a weak measurement, let the detector's position be very precise, but then its momentum is highly uncertain. In other words, there is a lot of noise going on there, such that if you make the measurement, you really don't know whether the result that you received, that you got, is a result of the particle itself, or whether this is due to some noise being introduced by the detector.
Hello.
So, the way...
יש שתי בנייני הנדסה.
זה הכל הולך ליוטיוב, כולל ההפרעה שלך. So, this is imprecise. You understand that this is an imprecise measurement. And in this case, you are not sure whether this is spin up or spin down. So, in order to overcome this uncertainty, you simply gather a large ensemble of such particles. And then you do a very nice and actually very simple and familiar mathematical trick. You have a zillion, say, an ensemble of n particles. Suppose that all of them have spin up. You let them go through the system, and then by summing them all up, now you are certain that you know what is their spin, and something very nice is going on here. Because you can overcome the noise, and in order to understand how you overcome the noise, just consider how an ordinary telescope is working. Whenever you make a measurement, in this case you observe a distant star, at each point you get the information coming from the star, the light coming from it, plus a lot of noise coming from other stars and atmospheric disturbances and so on and so on. You gather all the information in all those places and then concentrate it to one spot. And here, mathematically, something very cute is going on. Generally, information adds up, and noise sort of cancels itself. Actually, both of them add up, but in a different way. One of them adds up according to n, and the other according to the square root of n, such that if you have a large ensemble, the noise goes actually to zero, and your measurement is very precise. This is how telescopes work, ordinary telescope, this is how antenna work. You gather all the information together with the noise, you sum them together up, and you can eliminate, you can overcome the noise. Another thing which is really cute that goes on here is that the reciprocal disturbance that you inflict upon the particle also can go down to zero. You make a very weak measurement. So you get a very tiny amount of information. There is a lot of noise, you don't know whether this information is reliable or not. That means that also the disturbance that you caused to the particle is minimal. But once again, if you have a large ensemble of particles, the amount of information you extracted from them is huge, going almost to certainty, while the disturbance is very low. I would argue, and people agree with that this is a kind of way to outsmart the uncertainty principle. You can get some knowledge about a certain variable without disturbing the other variable with which it has some uncertainty relations. Can we wait with the questions to the end, and then, of course. So now the question is this, and as you see, Iyar, Cohen, and myself, this is one of the innovations. Actually, it's not an innovation, but of the advances that we introduced into this technique, although it was there all the time. The question is, how do we sum up? How do we do the summing up of the results? There are two ways to do it. Until now, most works in weak measurement summed up the results by just placing the detector, the measuring instrument, there, and letting all those myriad of particles go into it and let their combined effect be gathered there, such that you get one output. That's the easiest way. A much harder way, but as you will see, much more interesting, is to make each measurement by itself, make a weak measurement, then calibrate the detector back to its initial state, write down the first result, as uncertain as it is, make another measurement, write it down, calibrate it, and so on, until you have all the n measurements. What is nice about this method is that later you are doing the summing up by yourself. So the data is already there, you are only making the mathematical operation. You can also do something very cute, and you can regroup them. You can separate them and regroup them and then sum them up in a way which could be more efficient. And then we believe that we get something which I find, may I say, absolutely breathtaking. So here is what we do. For example, here is one work which was done recently, and we published together with Pagono a theoretical paper describing it. This is a Mach-Zehnder interferometer. So actually you don't know whether the particle took the right path or the left path. If you refrain from any measurement, you are going to get interference. That means that it will always emerge on the right because it preserves its momentum. If you make some measurements, of course, then you disturb it and you avoid the interference. In this way, when you have a double interferometer, you can do something pretty cute. You can make these two measurements weak, these two measurements, whether there is interference or not, also weak, and then the final measurements strong. If you did that carefully, you see something which is really amazing. Half of the photons by the weak measurements seem to, you get clicks on the left, and another half on the right. So you would say, fine, you made a measurement, and some of them went only on the right, and some of them only on the left. Oh no, because you see something very similar to interference. Almost 100% of them took the right path on the second interferometer, on the second Mach-Zehnder interferometer, which means that something akin to interference went on, which means actually that we managed to measure the superposition. It is not that half of them went this way and the other half went this way. Each of them took both ways, something which was considered to be impossible to measure within quantum mechanics, because actually you are measuring the wave function or the superposition itself. It was left intact, and here is the final surprise. You register all the measurements, and because they are individual, because we employed the second method of writing each of them down so we can follow them, we can prove actually, and this is something that can be shown very simply, that all those which ended up here are those in which the detectors clicked here, and all those which ended up here are those in which the detectors clicked here. So actually, you both know which path it took. You see the interference, and you can resurrect the which path information, something which is considered to be actually absolutely impossible within quantum mechanics. You measured two non-commuting variables within the same experiment. That's something very interesting. Steinberg and his group showed very interesting results within the setting of the double-slit experiment. And with this, I propose that we go now to the next stage. Because the results are very strange, may I explain something in classical physics or just classical probability theory, such that you will later understand what is going on when we go to the quantum level. I'm talking about coins, and here is Alice, and she has a stack of coins about which she wants to know whether there are heads or tails. Now, she doesn't have a good measuring apparatus, so she wants actually to find out whether they are fair, whether they are balanced. They have their center of mass is such that it's immediately, that it's exactly in the middle. And she also wants to know whether they are identical. So what does she do? A very primitive kind of measurement. She flips each of them, say, 10 times, and summing all the results, she is satisfied that probably all of them are fair and that they are all identical. You have an equal likelihood of getting heads or tails, heads or tails. This is a very inefficient measurement just by flipping. It's only statistical, but the important thing is that the results are engraved on stone. She does it in the morning and it's there. You can't change it anymore. That will prove to be crucial for what we want to prove later. So she believes that they are fair and balanced. On evening comes Bob, and he brings the best scales that you can think about and makes precise measurement for all the coins, and he finds out that the situation is quite different. Exactly half of them, if the n in this case is 1 million, exactly 500,000 are biased to the tails and the other half to the heads. That is, their center of mass is not exactly in the middle, but it is biased towards one of the sides, which is what confused Alice. But now he manages to separate it. So, once again, he writes down all the measurements individually. And then, of course, he can slice them by saying, these are all the results within all the million, which gave me heads, and these are all the results which gave me tails. Now he informs Alice not about his results, just the way he sliced them. He says, these coins, 3, 5, 7, 6, and so on, belong to group 1, and the other 2, whatever, belong to group 2. Separate them and now sum them up, because this is engraved on stone. She does that, and of course, we are not surprised to hear her saying, yes, Bob, you're correct. Indeed, now when I make the two averages, I see that all those belonging to one group are biased towards the head and the other biased towards the tail. Trivial, isn't it? Say goodbye to triviality. Because so we are not surprised to see that there is such a correlation. The bias has been there all along in the morning, and everything that all Bob did is what was just to discover it. That's fine. Shall we go now to quantum mechanics? Now, the ensemble which Alice has is 1 millionth in half particles, and she wants to know, this time, what is their spin. So she does a weak measurement in the way that we described earlier. And what she finds is that about half of them are spin up and the other half is spin down. Then she writes them, again she carves them on stone, puts it on the internet such that everybody can see. And then at evening comes Bob, and he is making a strong measurement. So he says, this is up, this is down, and now he writes his results, which are absolutely reliable, and in this case, you know which is up and which is down. Now he slices them again and says, these are all the ones which he gave me up. These are all the ones which gave me down. So these are the results. Would you, Alice, I'm not telling you which is up and which is down, would you regroup your data, which is already there, slice them, and now make the average, she does it and says, wow, you're correct. Indeed, all those belonging to one group are spin up, and all those belonging to one group by the weak measurement are definitely spin down. Now, trivial, isn't it? She just, on the morning, she made a measurement. She found out which is spin up and spin down. Her measurement was inefficient, but that is what they were during the morning. It is only that when Bob came, he found out the results after her and he just confirmed the results. That is what one would think naively about quantum mechanics. We are ready for the next move. So actually, this is what Bohm and actually Einstein always believed, that when you are making a measurement, you are finding something which was there already, and the measurement is only telling you the variable which was there. You don't have to talk about superposition and something that you are actually that measurement is breaking the superposition. You are just discovering the spin which was there from the morning, and you understand that there is something highly problematic with that, because what the two-state vector formalism says that indeed there is a certain kind of hidden variables, but of a very revolutionary nature. Let's indicate again the uncertainty principle, and suppose that on Sunday we made a measurement, spin measurement along the alpha orientation. At Tuesday we made a spin measurement along the beta orientation. There are uncertainty relations between these two measurements. And then suppose that we made a weak measurement on Monday. According to the two-state vector formalism, the state that you have on Monday is affected by both of them, both by the measurement of the past and the measurement of the future. Both of them affect the measurement that you carry out in between, which looks like a nice philosophical exercise, but that, most people would say, is not a proof that indeed in quantum mechanics you affect things backwards. How about the following move? So again, if you outsmart the uncertainty principle, you are supposed to get results which seem to offend your ordinary temporal notions, but is that something a rigorous physical result or a nice philosophical exercise? Let me only mention that some people do not think very highly about weak measurements or the TSDF in general, because they claim that you are talking about counterfactuals. People say, actually what these intriguing predictions tell you is, had you performed the measurement on Monday, you would get highly paradoxical results, but then you are not performing the measurement, because if you do perform the measurement on Monday, then of course on Monday this is the second measurement and your interesting prediction goes to the time in between. So you are supposed not to really perform a measurement. And then you can say, have we made a measurement, have we carried out the measurement, we would get these paradoxical results. This is how many people try to dismiss both the TSDF and the weak measurement. And now we believe that it is not going to work with the following move. Let's talk about the Iyar experiment. You all know this is one of the most revolutionary experiments in the history of quantum mechanics. One atom sends two particles to two distant measuring apparatus, and you're measuring their spin. So according to quantum mechanics, each of them is superposed, is both up and down. It is only upon measurement that they assume a certain definite spin, but then here you have a problem with relativity theory, because if it's only the measurement that forces the particle to lose its superposition and assume a definite state, then in order to comply with conservation laws, it must act instantaneously on the other measurement in order to get always spin up and down and never up and down, down. So this is the Einstein-Podolsky-Rosen experiment, and the question is, how do you explain it? And there are two ways to explain it. Is it as the Copenhagen and ordinary quantum mechanics assume, or is it as Einstein assumed, that in order to avoid a clash with relativity, you should assume that the spin has been pre-existing? All this talk about superposition is just wrong, and in some very profound way, the particles are either up, down, or down, up, and you only discover that. Or, if you take quantum mechanics, you should think of them as really superposed, and you don't detect the spins, but you determine them, which in this case involves some action at a distance and all the clash between quantum mechanics and relativity, which is one of the greatest open questions to theoretical physics. So far this is a nice philosophical exercise. There is not much physics in it because no physicist would bother to carry out the experiment for the simple reason that both theories, both philosophies give you the same prediction: up, down, down, up, and never something which violates conservation laws. Along came John Stuart Bell and gave the following proof that indeed it is ordinary quantum mechanics which gives you the correct interpretation, because he says, let Alice and Bob, when they carry out measurements, not measure them along the same orientation, but take some different spin orientations chosen such that the uncertainty relations between them would be quite noticeable, and then you're going to notice something interesting. Alice and Bob decide at the last moment which of the three spin orientations they can choose. He can say, I'm going to measure alpha, she says, I'm going to measure gamma, and they make the choice at the last moment. Then if you do that and repeat the experiment several times, you get something very interesting. The correlations between the results depend on the relative angle between the two magnets. But then if that is the case, then there is no way that the two spins could be pre-established. If in order to give you such results, sometimes correlated, sometimes anti-correlated, the amount of correlations depends on the relative angle between the two magnets. It can be shown by a fairly simple mathematical exercise that in order to give you such results, each particle has to know at that moment which was the choice made by the distant experimenter, what was the result given there, in order to know in which case to give correlated results and in which case to give uncorrelated results. So with John Bell's theorem, that was the first and very strong proof that indeed something non-local goes on within quantum mechanics. Later came GHC, Ringberger, Horn, and Teininger, and produced an even more convincing experiment of this kind. But for us, we can be satisfied that indeed what Einstein feared the most, that there is something non-local going on within quantum mechanics, acted like a boomerang, and it proved that indeed quantum mechanics is doing what everybody feared and actually doing something which is very fishy from the viewpoint of special relativity, and this is still an open question. Now we suppose the following, and with this I'm almost done. We repeat the same experiment, and in this case Alice gets now an ensemble which is not points, which is not spin-half particles, but EPR pairs. These are pairs which were produced by the same atom, so that means that if we carry out the EPR experiment on them, we will see that there was something non-local going on between them. So she has such pairs, and in the morning Alice performs 3 weak measurements on each particle and repeats it, say, 3 times. So all in all together, she is doing 18 weak measurements. And she gets the results. And once again, she carves them on stone. And what she gets is only this dull 50-50%. Nothing strange about that. Now, Bob, on evening, he wavers all the day. He is not sure what he is going to choose for these 2 measurements, because he is going to carry out 2 strong measurements. So he says, I think I'll measure alpha on the right. You know what, why not beta? So there was a bird flying outside, so it will be gamma on the left. And then I heard something in the news, no, why don't it be alpha? So he keeps wavering all the day and debating with himself, but then evening comes and he makes a decision. Remember that the decision is completely free. Nobody knew what his decision is going to be, neither Bob himself, because he just kept playing with it, and To the extent that there is something like free will or free choice, he was exercising his free choice. Physically, there is no way that we know that we can predict what he will choose. But he chose it. Once he did that, so he says, you know, these are the two measurements I'm going to carry out from this pair. Now the same thing goes. Let me just remind you what he does. When Alice did her weak measurements, she carved them on stone, and everybody could see them on the internet. When Bob was making his measurements, throughout the day, everybody could read his blog and follow him. He's making this decision, that decision, he's not sure, people are telling him, you know what, take alpha, take beta, and then people write emails to him, SMS, and so on, and then we all see that he made this decision, and he carried them out. Now he gets the results. And of course he slices them. And he says, because these are exact measurements, he can see that in this, this is what they got. Spin up and spin down with each measurement that he carried out. And now he repeats his feet and sends Alice. He doesn't tell her which was the spin orientation. He doesn't tell her which was the result. See how objective it is. He only tells her, this is group 1, this is group 2. Now, recalculate them, separate them, and sum them up. And what she gets is just this. Once he did that, and she is slicing her results, immediately, three of her measurements on each side stand out. The correlation is perfect with that of Bob. So she says, aha, it was B, and you got, in this case, spin up and spin down, spin up and spin down. This is precise. Then he says, he gives her the way to slice the measurements. He doesn't tell her that this is gamma. He doesn't tell her which is up and down. He just says, slice them according to this criteria. And once she does it, immediately 3 others on each side stand out with perfect correlation to what he did to his results. Now, you may say, what's the fuss? She made a measurement. She got some results. Bob later made strong measurements and got. He just repeated her results. Already at this stage, you can see that there is something which quantum mechanics apparently forbids you completely to do. You are carrying here 3 measurements which have uncertainty relations between them. That means that if you carried out measurement beta and you got a collapse, and then there was gamma and alpha, there is no way you're going to get again the same beta. You disturbed it. But this is not what happens. All 3 betas give her the same result. All 3 gammas give her the same result. So it's already revolutionary in the sense that you made measurements, the measurements repeated one another without disturbing each other. But then, of course, we know that even that could not be the case, because remember what Bell's inequality tells you. Actually, it proves, in order to prove non-locality, Bell's inequality amounts to a mathematical proof that there could not be pre-existing spin values with the spins prior to measurement. Have you been carrying out real measurements on them, then they'll stop being entangled, and there will be nothing non-local going on. But there was something non-local going on in the evening measurements. You could prove by Bell's inequality that they affected each other instantaneously, which means that there was nothing in the morning which was a predefined spin value within the particles. Can you see the contradiction? On the one hand, Bell's inequality, Bell's theorem, which is one of the strongest and simplest theorems in the history of physics, proves to you that when you are making measurements of this kind, and actually you can generalize it to all quantum measurements, it is not that you find out a predefined spin which was already there. It is the measurement which actually forced them to assume one of these spins. So that means that it is only at the time which Bob made his measurements that these spins came into existence. On the other hand, you know that the causal relations between weak measurement and strong measurement go only one way. A weak measurement never affects a strong measurement because it's not really a measurement. It is a weak measurement, so it leaves the particle completely superposed. It is the strong measurement which actually locks it. Has it not been the case, this experiment would fail. You would lose correlations already here, and you see that the correlations remain until the experiment in the evening, in which you do see a non-local effect going on between the two particles. How can we explain that? Within the TSVF, this is the most natural thing, because this is what the TSVF has been arguing all along for many years. You want to understand the mystery of quantum mechanics. How is it that the measurement of one particle non-locally affects another particle? You have to look at it in 4 dimensions. Think about the time dimension, and then you can understand, which is perfectly consistent with the TSVF. The measurement that you did, say, on Monday, affected the entire history back to Sunday, to the common atom, to the common origin between them, and then came back to the present via a kind of space-time zigzag, going to the past and then coming back, and the same with the other measurement. So part of the mystery, I would say, is lifted if you are willing to swallow this, if you are willing to accept this very serious blow on your ordinary temporal notions, that indeed in quantum mechanics every measurement is somehow affecting the past. To this day, there was no really proof, a very rigorous proof, for this extraordinary claim. People only say that it's a beautiful explanation, it is consistent, it is parsimonious, but that's about it. We believe that what we proved here, through the most rigorous reasoning of Bell's inequality, plus what is accepted within quantum mechanics, that the causal relations between weak and strong measurements are only one-sided. Actually, we think that this is the first time in which we can see that indeed quantum mechanics, the quantum measurement, affects the system not only to the forward time direction, but to both of them, which means actually some kind of affecting the past with all the paradoxes which ensue after from such a statement, and that actually this is a completely new way to understand the quantum mysteries by accepting that there is something very fishy going on here in terms of space and time.
So the TSVF is an alternative and consistent...
Just let me say that I'm done. Yes, so time for questions.
So the TSVF is an alternative and consistent way to approach quantum mechanics, right? So am I
right?
Okay. And it allows you to explain this paradox which you cannot explain with ordinary...
Right. Let's, I know that I've been quite quick, so let's review again the results in order to see whether we can look for a more conservative way.
Can you repeat the progress of the experiment? Because I
Sure.
exactly understood what you measure and what Bob measures, what S measures.
This is morning. Alice takes one EPR there after another. And on each of them, she performs 3 weak measurements along
In different angles.
Yeah, along these 3 angles. Alpha, beta,
Random
gamma.
or
Random. Let's make it completely random. Okay.
Okay.
So
for each,
9
for each pair, 3 measurements in 3 different directions.
Sure. Okay. And then she gets her results, which are
She
highly
writes the results up, down, down, up for
Right.
each measurement.
and they're highly inaccurate, of course. So, but she writes them down, carved on stone. Okay. So she's performing all these three measurements and getting results which are completely meaningless. Half and half and half and half, because she's not slicing them. Now, at evening.
It won't be half and half because in different directions that there will be some kind of correlation according to Bell inequality. Right? If you measure alpha and alpha, then you get the exact correlation. Up and down. Because if you are measuring alpha and gamma, then there will be some 30%.
Right. But let me remind you that in EPR, when you look only on one side, you see half and half.
Yeah.
And exactly here. Okay, so she doesn't see correlations yet when she looks at each of them. Actually, she is not supposed to see correlations even when she looks at both of them, because this is weak measurement. Actually, this is very interesting. What do you think, David? If she observes both of them, she won't see anything no longer going on. Which is very, I thank you for this question. Because when she looks at her results in the morning, she says, this is half and half, this is half and half. No matter how I slice them, I won't see any correlations.
If you take the two measurements of the same pair,
Alpha and alpha, in case there was beta and beta or alpha.
no, the same pair.
Right,
If you took, let's say, alpha and alpha,
right.
even if it's a weak measurement, you will see up and down or down and up.
She wants it. You don't know how to slice them. Remember, when you have weak measurements and you write this down, all you can do is sum them up together and you get this down 50-50. You don't know how to slice them. So I thank you for this comment.
Okay,
This
so
is-
for each pair, you will see no correlation at
No
all.
correlation at all.
And of course, on each side, you won't see any correlation.
Right. But moreover, if she looks at both of them, she won't see any correlation. Even in the case in which she was measuring alpha, beta, and gamma.
Now both measures,
Now we-
at the evening, both the sun is two directions, and he measures the same pairs.
Yeah, right.
If there were three pairs, he
Yeah.
measured the three pairs, and he got
How many?
6 measurements. N pairs, he got 2 times n measurements.
Right.
And she got 2 times 3 times n.
She has many stones on which she carves the result of
But for each particle, she made, let's say,
18 in this case, because
18 measurements.
she made 3 measurements, repeated them 3 times, and she did each of them, she performed each of them on the 2 particles. So you have 18 weak measurements for each.
For each particle. For each
Right.
particle.
And on the rock, you have 18 rows, which are absolutely meaningless. Up, down, up.
Now, what Bob gives her.
Now Bob decides, you know what, I'm going to measure beta and gamma. He makes the same measurement on all pairs. We are making life easier for him because he
So he's getting 2 n results, up, down, down, up,
Right,
down.
right.
Okay.
Now he writes them down. Now he knows how to slice them because they are precise. This is up, this is down, so he says all these measurements belong to group 1, and all the other measurements belong to group 2. These are definitely spin up, each of them, and these are definitely spin down. Now he doesn't tell Alice what are the results. He just says this is group 1.
You don't know what direction that you should.
Right.
Okay.
All he tells her is just slice them and they are carved on stone. Can you fake this? Sharing Bob,
Wait, just a minute. Then Alice compares it with her
rather than summing them all up, now she has 2 groups.
But
So-
for each
Raw.
measurement that Bob did, she has 18 measurements.
Right.
So
Because she has the serial number of each of them.
So what does she do with the...
She slices them because he says to her, measurement number 1 belongs, I'm not telling you whether it's up or down. And I don't trust your own result because it's weak. It's highly noisy, it's highly inaccurate, so I ignore it. All I tell you is put 1, 2, 3, 5,
So like
8
she
in one
puts
row.
all the results from alpha in one row and sees
She doesn't know even that
correlation.
this is alpha, but she
No,
makes
when
it
she did alpha.
right.
And all the results that when she measured beta.
Beta.
And
And
all
all
the
the
results when she measured gamma and sees that when at the row of what she measured gamma, there is a correlation with the result, with the grouping of both.
Precisely. The measurements stand out immediately and she says, I know this was beta. You didn't tell me, but I see perfect correlations with this.
Why is the other side beta? Because we get the other grouping.
No, what she did was she took each particle and measured alpha, beta, gamma. Then another, again, alpha, beta, gamma. 3 times.
Now she takes the grouping of Bob.
And she slices all the 18 rows that she has. And out of them, I would say 3 here and
But
3
all the beta on this side
side.
will pop out.
Right, and also all the metals on this side you are correct with inverted speed.
Inverted spin.
You are correct. But then they stand out. And then she said, aha, I know, you didn't tell me, but you measured better, didn't you? He said, oh yes, how did you know that? And then she said, now let me tell you which is the result you received for each of them. You didn't correct it for 1, 3, 9, you got up. And for the others, and she gives him the serial numbers. And she says, wow, you were correct. To the last of them.
But it will be a statistical result. It won't be 100% correlated
It can
with
approach
this.
certainty if your n is large enough, it approaches certainty, because she says
Okay.
the correlation is so strong that it indicates that all of them. Remember what I showed in the
But
beginning.
then why are you surprised?
Okay, let me
Why
tell
do
you.
you say that it writes back the history?
Because one way to make it trivial is to say, what do you want? She made a measurement.
It was there all the time.
Yeah, it was there all the time. So she made a measurement. But tell me, what happens when you take two EPR particles and perform measurements on them?
Yeah, but it's not that.
Wait a minute. No.
You break the correlation.
Yeah, but can you measure them again? What happens to them after you
They
disentangled?
they
Do you see that they are disentangled here? I mean, they've been entangled here. They keep being entangled here, right? Once she has the gammas, they're entangled here. They keep being entangled here. Between them, there was alpha and beta. You understand that there is already a revolution in quantum mechanics in this case. Yakir doesn't like to say that, but you are actually outsmarting the uncertainty principle in a way that nobody dreamed.
But the key said that already when his article about the paper about measuring the wave function. It's like exactly like measuring the wave function. You many strong and many weak measurements.
All we did in this work is to make it more convincing. Nothing in which Aaron did not say for the last 20 years.
But I don't see why do you see that it goes like back to
Okay.
real
So,
history?
There is one way that you can avoid temporal paradoxes and say that we managed somehow to outsmart the uncertainty principle and that we just measured spins which were already there. But you can't do even that for the following reason. What did Bell inequality tell you? There is no way in which you could be prepared for whatever choice will be given to you later. So perhaps I skipped that part of the proof, so let me repeat what Bell did. Bell said you have two particles, on which you're going to make two measurements. If Einstein was correct, you would expect that these two particles would be prepared in advance for alpha alpha, alpha beta, beta gamma, beta alpha, and so on, for all the combinations. It is mathematically impossible to do that. Because if you don't know which are the two measurements that Bob is going to choose freely, and you can't be prepared for all of them because they contradict one another. That's, I think, the most important part of my talk. I should say it earlier. So I thank you for this question. So it's mathematically impossible. It's not physics, it's mathematics, logic. They can be prepared in advance. One way to skip it, but then I don't know whether it's between typhoid and cholera, as to say in Hebrew. One way to avoid the paradox is to say that they already know what Bob is going to choose, and then they prepare themselves in advance for that. Do you find it more?
Another possibility.
Yes. Do you find it less disturbing than what I said?
What I'm saying is that you're not how the weak measurement has to be weak. How weak is to be weak in order to be called weak? Where is the boundary? You can say that above this
It depends.
it's strong and below this it's weak.
It depends on the inverse of square root of n. In order to be
What do you do? Statistically weak?
no, the interaction, the Hamiltonian depends on the inverse of depends on 1 over square root of n.
What is n?
The number of particles in a
So the
sample.
statistical. The number is statistical. If I do only one measurement,
It's not good.
there's not good. It's two measurements,
No.
not one.
You need n.
So again,
Once you see n, right there. But then you went back to each case, and you know it with certainty. Yes, you did it statistically, but once you did that, when you go back, let me remind you, how do you perform the double slit
So
experiment?
again, so this threshold is statistical. If I do more measurement, I can make this.
There is a point.
Yeah, then I think exactly what you're in the following sense. When you make the double slit experiment in its quantum version, you have one photon going on every 5 minutes, and so on. You can see the interference only statistically, but from that, absolutely rigorously and logically, you have to conclude that each individual particle in some strange way took both paths. You understand the strength of the quantum mechanical reasoning. You can do something statistical, but the results sometimes oblige you to make a very weird conclusion, to draw a very weird conclusion for each individual case. So That's what we have here. Although it's statistical because of the large N, now the statement that you are making about each individual case is very strong, very rigorous.
Sure, but part of the system is the measurement itself. No matter what you say, weak or strong, the mere fact that a measurement has been introduced into the system is not the same as what you're talking about.
Fine. But then what do you get here? Let me follow you. You say the following: I take a quantum mechanical system, which is a problem.
What I'm actually saying that by our intellectual means or whatever we have, even instrumental means, the system is totally unapproachable unless we start to do some experiment. You know, one way that you can prove me the whole thing, that if you could, in a way, or just hypothetically, you could turn it into something macroscopic that I could visualize it or do something with it. But which is, of course, a dream. You can never do this.
No, wait, but tell me, Mayor, what could be more macroscopic, for God's sake, than something carved on stone? Each individual result is now recorded, and it's there.
Yes,
And you look at it and you say it's absolute rubbish. There is nothing here. All I do to you during the evening is something very simple. Just divide it. You can't fake it. Actually, the interesting question that you guys should ask is, can somebody fake it? Can Bob not perform any measurement and just deceive Alice and say, I performed the measurement, whereas he did not? And this is how I slice them. Now you slice them and you will get all this interesting web of 18 results which so nicely fit one another. Can he do that? Yes, he can. He has to use enormous computation in order to do that. And remember one thing, in order to do that, he has to know each individual result of Alice. And then, after huge computation, he can do that. It's enough that Alice carried some measurements that she did not tell him, that she hides, that when he sends her the way for slicing, she just brings them and he says, he was cheating. On the other hand, if the measurement is genuine and he is not lying, he doesn't have to know anything about this. He can
But it
just...
works the other way around. She can do the same computation, right, and looks for the one which are eventually the sequencing that give her a large correlation.
You say that, yeah. If Alice takes all her measurements and uses a very strong computer, yes, she can do that.
No,
Of course she can.
because the results at both ends are random.
Right.
He measures better. Sometimes he finds up, sometimes he finds down. Then he finds the slicing. Only then he could go back to Alice and show her the slicing.
No.
If
He would be able to tell him that if he measured better, this and this would be the ones.
Number of options.
She doesn't know what he's going to
Go
measure.
by-
She can tell him, if you measure better, this and this particles will give you great, this and this will give you great. This is what she can tell you. Of course, she cannot tell him what he's going to measure. But once he measures him, she can tell him.
בוא נעבור לעברית, אני חושב שאני צריך לעבור לעברית, כי אני חושב שהדיון הוא מעניין.